Good afternoon. It's great to be here. I came from Israel, so really excited to be here. Before I'll tell you a little bit about myself and about what we do at MyHeritage, let me ask you guys a few questions by raise of hands. So how many of you have a Kafka cluster up and running on your production environment? Wow, that's impressive. All right. And how many of you have used Google BigQuery, any kind of basic experience? All right. And is there anybody in the audience that tried to load data from Kafka to BigQuery? OK, great. So for those of you who did not, now would be a good time to start. This is from Kafka to BigQuery. My name is Ofir. I work at MyHeritage. And this is our journey of loading billions of events every day straight to our analysis system in near real time. All right, so we're data engineers, after all. So one of our main goals, if not the goal of a data engineer, is building data pipelines. So how do we make a great data pipeline? Well, I'm going to argue that making a data pipeline great is achieved by building a reliable pipeline. And when I'm saying reliable, I mean correctness of your results. And those of you who dealt with stream processing know that can be a challenge. You also want to build an efficient pipeline. You want to give your stakeholders the ability to make their decisions and make them on time. And you want to have the ability to scale to millions and billions of events. All right, I want to mention a few considerations for building data pipelines. Of course, there are a lot, but here are just a few I've decided to focus on. So we talked about efficiency. So we're talking about end-to-end latency. And when I'm saying end-to-end latency, I mean the time that is passed from the creation of an event at the source system until the time this event is fully loaded and ready to be analyzed in your data warehouse. Second consideration is data structure and storage format. We've used Apache Avro. Apache Avro is a compressed binary format. It also has schema evolution. And it integrates perfectly with Kafka with the schema registry component. So we're going to talk about this later as well. Third concept is data partitioning. Data partitioning is the way you store your data in your destination system in a way it can be easily accessed later when you query. In systems like BigQuery, which is a pay-as-you-go system, this is extremely important because you don't want to do costly full scans. You want to know exactly what are you querying. And last, the concept of reprocessing of all data. So we tend to forget to save our historical data. It's easy to forget, but today the storage is relatively cheap. And if we have bugs in our systems, or perhaps we have new features that we want to add, it's very important to save your historical data for as long as you can and be able to replay it later. This session is based on a case study of MyHeritage data pipeline. MyHeritage is all about connecting you with your relatives. You build your family tree, and with it you can discover, preserve, and share your family history. Moreover, you can take a DNA test and reveal your genetic secrets. So what kind of information are we collecting at MyHeritage? First, our user base is creating user activities of many different types, which we send to different Kafka topics in order to control their scale. And these events come from multiple sources, from web, from mobile, and from desktop. Then we're talking about requests arriving to our servers. This can be page views by users, pages that are scanned by bots, or API calls arriving to the servers. And last, we're collecting change data capture events. Anybody here doing change data capture? All right. So change data capture is the way you collect your database record changes. What we do is we collect every insert, update, or delete record from our databases, and using stream processing, we connect it to user context. We're connecting it to request information, to canonical URL, to session params, and so forth. So I want to say a few more words about what we do with change data capture, because I think it's quite unique the way we analyze it. Meet Linda. Linda came to Kafka Summit today, and Linda is using your app. And after the summit, Linda decided she knows enough about Kafka, and she decided to change her job description in your app. And she decided she wants to call herself a Kafka specialist. So Linda triggered a simple update statement to your database, setting her job title to Kafka specialist. And this is basically simple this far. So now the challenge is collecting these record changes with change data capture tool. You can use Kafka Connect to do this for multiple databases. We actually did it with Maxwell, which is a utility to collect those change events that comes to the database replication logs. I think Jay Krebs talked about it a bit in his session today. So we collect these record change events, and it looks something like this. First, you have basic information about the change. The basic information contains of the database name, the table, the type of the change, it was update statement, and the timestamp of the request. Moreover, we have here a database connection ID. Remember this field, as we'll use it later. Then we have every field in the specific record, not only the field we changed. So let's imagine in the users table, these are all the fields we have, and including the last field, which is a Kafka specialist. And then we have another field here of what have we changed. So this is great. We have simple raw data change, but what can we do with it? Because there isn't really anything interesting here in terms of analytics. The challenge here is to connect it with request information, with user context, and so forth. So let's see how we do that. First, in each and every request, we collect the request information to Apache Kafka. And this looks something like this, a request ID with a timestamp and the user details, which was the user that was invoking the request and the IP of the user. And also we have URL information, such as canonical URL, full URL, and parameters. And then we have HTTP information, such as the method, the status code, and the request and response headers. Now all we have to do is connect the dots, and we do it with Kafka Streams. So we have the first stream, those change data capture events containing all database record changes, those inserts, updates, and delete. And we have the second stream with the request information. And then we want to join it with Kafka Streams. But in order to join it, we miss a third stream. And this stream actually binds the connection of the database to the request ID that was part of the request. And then we can join all these three streams together and create a final enriched CDC events topic. Does this make sense to you guys? Great. All right, so I want to take a step backwards and talk about the high-level architecture of our system. So we have Apache Kafka standing at the center of the system, basically de facto the standard today for a streaming platform. We chose Kafka because it has low latency and high throughput, and we can build a real-time data pipeline with it. Moreover, it's durable, it's fault-tolerant. We started with version 0.10, and now we headed to 1.0 to get exactly one semantics. So we send to Apache Kafka all those requests we discussed earlier. Those requests coming from multiple sources and change data capture events and user activities. So Kafka basically separates between the creation of the events to their processing. And we send all these events to Google BigQuery. And from now on, we're going to talk about how we do that. All right, so let's talk about Google BigQuery in a nutshell. Still, there are some that didn't know it. So Google BigQuery is a cloud data warehouse, fully managed by Google. Google will build the server, will install them, will handle the scale automatically for you. So as your load increase or decrease, Google will handle it. So basically, it's very simple to use. As I said earlier, BigQuery is a pay-as-you-go system. You run native SQL queries, and you pay for the data you scan. You pay $5 per terabyte of data you scan. BigQuery also has streaming support, and that is one of the most important considerations of our choice of BigQuery over the alternatives. So we wanted to build a real-time data pipeline, and BigQuery provides an API to stream the data in and have it ready for analysis within seconds from the creation of the event or from the actual occurrence of it. BigQuery has a daily partitioning feature. The daily partitioning is very useful for partitioning your data. But when you use partitioning, you have to remember these two concepts relevant to partitioning. You can partition by processing time. And processing time means wall clock time. It means when the event was observed by the processing system. So this is actually easier to implement, but it may result with data arriving to the wrong buckets. If you want to achieve 100% correctness, you want to go to event time. Event time represents when the event was actually occurred at the source system. So most of the time, this is implemented with a field, like we did. The field is embedded in each and every record, and it has a value of the actual event timestamp of the request. All right, so I'm going to start describing our data delivery journey. I'm going to mention 4 techniques of loading data from Kafka to BigQuery. And I want you to be judgmental as I talk about these techniques, because each and every one of them has its own trade-offs. So you want to choose carefully. All right, so our first attempt was doing batch loading. We didn't even try to stream the data in. We gave up latency, because we had some experience with batch, and we didn't want to start with something we don't know. We wanted to feel the system. We wanted to feel the data structure and the storage format, and try to work with BigQuery for the first time. So batching seemed like a trivial solution. So how did we batch load to Google Cloud Storage? This is a 2-step loading process. First, you have to load the data to Google Cloud Storage with Secor. Secor is an open source utility provided by Pinterest. And this utility allows you to consume data from Kafka and load it to an object storage system of your choice, like Amazon S3 or Google Cloud Storage. And the next step here is actually loading the data from Google Cloud Storage to BigQuery native tables. This is not a must, because in BigQuery you also can query the data that is stored on Google Cloud Storage. But if you want to achieve better performance, you want to load the data to the native tables of BigQuery. So here's how it looks. First, you have Secor, listening to your topics you defined in Apache Kafka. And in Secor, you define a threshold. For example, every 10 minutes, take everything you've consumed from Apache Kafka and send it to Google Cloud Storage. Then you can run some loading script or even use BigQuery API or RESTful API to load the data from cloud storage to BigQuery native tables. So we decided to do it with a script, and this is the script. It's actually a 1-line script that was splitted here in order for you to be able to read it. So what are we doing here? This uses BigQuery CLI and does BigQuery load, please load the data that is stored in this specific bucket of Google Cloud Storage, take it from the specific destination, and load it to this table, this BigQuery native table, within the specific partition I've defined. All right, so a couple of trade-offs of using this technique. First of all, we have multiple partitioning options. We can use ingestion date, which is when the event was observed by Secor, and this is equal to processing time. Or if you want to achieve better correctness, we can do record timestamp. That is telling Secor within configuration, my event timestamp is stored in this specific field, and load it to BigQuery or load it to Google Cloud Storage. Next, we're talking about concurrency and scaling. You can define statically the amount of workers you want to work with at the core, and this can be raised up to the number of Kafka input partition topics, up to the number of partitions in your topics. All right, so a few drawbacks of this technique. As we said, this is a two-step loading process. The core wasn't designed to send the data directly to BigQuery native table. So you have to go through Google Cloud Storage and then send the data to the native tables. So you have to give up latency in this technique. All right. So our second approach was actually using streaming and having a real-time latency or near real-time latency. As I said earlier, Google supplies an API that using it you can load data to BigQuery and have it available for analysis within seconds. It comes with a cost and a quota limitation. The cost is 5 cents per gigabyte, and the quota limitation is something like 100,000 records per table. And you can also talk to Google if you exceed that. We didn't exceed that. And another advantage of this technique that there's no preliminary step here. You can load the data directly to the native tables, and you don't have to go through Google Cloud Storage first. So you have to consume your data from Kafka. You can either do it by implementing your own do-it-yourself Kafka consumer, or use your favorite streaming framework as we did it. Either way, you have to send the data to BigQuery Streaming API, and this is actually the most complex part of this technique, because you have to consume the records and maybe put them in batches in order not to send an API call for each and every record. And you have to handle concurrency or let the streaming framework do it for you. And you also have to handle faults and errors from the streaming API of BigQuery. So what we did is we used Kafka Streams to load the data. So this is a coding sample. This is actually a working code. Notice that this is 10 lines of code. So you can take these 10 lines of code and run it. And it runs in the normal main Java function. So all you have to do except this is define the dependency to the Kafka Streams library, and you're good to go. So what are we doing here? Let's go through it step by step. First, we have the basic configuration. This is the minimal configuration I've had to define in order to make this work. You're telling Kafka Streams where your host and port is, and then you have to tell the Kafka Streams your app ID. And this is actually more interesting, because this application ID is connected behind the scene to Kafka Consumer Group ID. And it gives you fault tolerance, and it gives you redundancy, as you can run multiple instances of your code, and the workload will be split between them. So this is quite a unique concept. Up next is the actual stream processing pipeline. Let's see what we're doing here. First of all, we're taking all the data from a topic called my topic. Then we're telling Kafka Streams, please take all the records that are called take me to BigQuery, and for each and every one of them, call a function that I've defined here, which you don't see the implementation right here, that send the data to BigQuery. And as I said, this is the complex part of the technique, because as you can see, using Kafka Streams is quite easy. And then at the end, you tell Kafka Streams, please take the builder and configuration that I've defined above and start streaming. So there you go, 10 lines of code, working Kafka Streams application. All right, so a few trade-offs of working with BigQuery Streaming API. First of all, you have low latency. As we said, we're sending the data in near real time to BigQuery. Then you have complete control in your hands. You're the one that implementing the API and using it. So for those of you who want the control in your hands, you have to remember that this control comes with the responsibility of building a robust service and handle streaming errors and record batching in order not to perform an API call for each record. So this is something that in 2018, you think there's maybe a better system than doing that instead of using the API directly. And there's when Kafka Connect comes to the rescue. So what is Kafka Connect? Kafka Connect came to deliver data in and out of Kafka. So it has multiple connectors. You can easily connect it to file system, to databases, to key value stores, to search indexes. Basically, any system you can think of was already implemented. And if not, you can create your own connector, which is quite an easy task. We use WePay's connector to sync data to BigQuery directly. And you also get redundancy and scaling for free. This means that you run multiple instances of your connector. You can run them on a single node, or you can run them in distributed nodes and build a redundant system. And the workload will be split between all your workers running your connector. So this is how it looks. Quite simple. You consume the data directly with Kafka Connect from Apache Kafka and send it to BigQuery. Very easy. But for sure, there are trade-offs. So let's talk first about the pros. This is a plug-and-play solution. You don't have to write any code whatsoever. You only define in the configuration the input topics and the names of the BigQuery tables that you want to send the data to. Second, as we described, this is leveraging Kafka for scaling and handling failures. For example, only after a successful write to BigQuery, Kafka commit the consumer offsets and continue to the next message. And next, we're talking about an automatic creation of BigQuery tables. If you use Apache Avro, your data and your schemas will be stored in the schema registry component. And what the connector that was implemented by WePay do, it takes the schema from the schema registry and it translates it to the schema that is needed by BigQuery to create a table. So you don't even have to create the tables on your own. Plug and play solution, and you're good to go. And the downside, in the implementation of WePay, we're talking about partitioning by processing time alone. This means that if you have late data arrivals, they may arrive to the wrong bucket. And up next, as this is a Kafka Stream ecosystem solution, you need to process your data from Kafka. So if you store your historical data in another system, you first have to ingest it to Kafka and then replay it. So this is also something you have to consider. And last technique is streaming the data with Apache Beam and its Cloud Dataflow runner. All right, so Apache Beam will give you a unified model for both batch and streaming. That means you write your code once, and then you choose by configuration if you want to batch the data or stream the data. Second, this is a portable platform. So it works with multiple execution engines. You write your code once, and then you can choose where do you want to run it. You can run it with Apache Apex, with Flink. You can run it with Spark, and you can run it with Google Cloud Dataflow workers, which we did. So the managed Dataflow workers means that your pipeline will run as a cloud job in Google servers. So Google will handle the scale automatically for you, which we didn't have so far. So this is how it looks. Apache Beam is consuming the data from Kafka and rerun it within Google Cloud Dataflow workers in the cloud and sending the data to BigQuery. All right, so this is an example for using Beam and handling a page view event. And with this page view, we want to have the ability to send it either to a bot page views table or to user page views table, because different queries are applied for each of every one of them. So what we do here is we determine the table dynamically. We take a specific value from the record and decide whether this current record is bot or user. And then we decide upon the table dynamically. Similarly, we can determine the event timestamp and partition by the actual event content. So we take the value from the event that is embedded within it, and we determine the partition to send the data in Google BigQuery. So this is a Beam example. This is not a full example, as you saw with Kafka Streams. but you can definitely use it. All right, so a couple of trade-offs when using Beam. First, Beam has a unified model for both batch and streaming, and you can run it with multiple runners. Some runners are better for on-prem, others are better for the cloud. So this gives you the flexibility you may need. And as we described, Dataflow Runner has its advantages. It auto-scales, it runs in Google. So if you're talking about transferring the data to BigQuery, this can be very close to that. And you can also process data from different sources. You're no longer obligated to Kafka as your input. You can store your historical data in another system and push the data to BigQuery from there. And a few cons for using Beam. First of all, Google handles, when you use the Dataflow Runner, Google handles the flow, raises and removes workers according to your load. So this comes with a cost. And second, this is not a part of Kafka ecosystem solution. So Apache Beam is relatively a new kid in the block. Its first stable version is about 8 months old, version 2.0. So you also have to consider that if you decide to use it. So this was our choice. We chose to go for a full Kafka ecosystem solution. We process the data with Kafka Streams, send it to other topics, and then use Kafka connectors to stream the data to BigQuery. All right, so a summary slide comparing batch and streaming and the different techniques that we applied. The delivery time is delayed in batch and almost instant near real time for streaming. The cost is free in batch and stands on 5 cents per gigabyte in streaming. Loading step. We talked about a 2-step loading process in batch. You first have to load the data to Google Cloud Storage, and only then you can load it to BigQuery. And in streaming, it's a 1-step loading process. And the data partitioning and reprocessing is depending on the streaming framework you choose. So you can take a picture of the slide, and we'll move on. All right. So I'm going to sum up with this. Use Kafka, use BigQuery, and choose the right technique for you. Remember that there's always a trade-off, especially when you build the near real-time data pipeline, when tools are evolving every day. So choose carefully, and you'll be able to build a great data pipeline. Thank you very much. And please rate the session. Thank you. Question, please.
Sorry.
Please.
Please do use the mobile app. It really helps us evaluate the sessions, help us build a really strong conference. So that was excellent. Thank you very much.
Thank you, Robin. Any questions?
For some questions.
Yes, please.
Well, you started out with, you started out with change data capture. And
correct.
What happens in such a flow when you refactor the database? So the change looks completely different.
All right, so good question. Question about refactoring the database with change data capture. So actually, as I said, we're using Maxwell, which is a replication log-based utility that listens to the replication logs and sends them to Kafka. It also gets the database alters, the alter table, so forth, within this change. So you can use it for your pipeline and have it all managed there. Yes, please.
What was the question?
Hey, so
Hi.
I noticed that you're using a BigQuery and Kafka, but the main question, why Kafka not pops up
All
in
right,
Google?
good question. So actually, the main reason that we chose Kafka over alternatives such as PubSub is that because we had previous experience in it in other systems. Moreover, it gave us the ecosystem that we needed. It gave us the retention. It gave us the streaming pipeline so that you can also achieve with Google Cloud Dataflow. But mainly, this is what we had experienced at. So we were used to working with Kafka, and it proved itself all the way through. At the end there.
Thanks very much for the presentation. You mentioned that in the end you picked up on
connector, Kafka Connect, to ingest data into BigQuery. So it means that you actually picked up on using processing time forced you by the connectors. So there's no way of using your own timestamps from events eventually.
All right, I don't know a way of using event timestamp with this specific connector that we've used, but you can also contribute to the community and improve the connector and have event time capabilities within it. The reason we chose to handle processing time and gave up 100% correctness in our case is that this is an analytics pipeline. So we feel all right if 99.999 of the records will be fine, and then perhaps a few will be sent to the wrong bucket. Of course.
So just to add to that, and a shameless plug, I'm doing a talk tomorrow. You can actually use something like KSQL or Kafka Streams to actually change the timestamp of the messages passing through. So you could use the same connector with a different timestamp if you wanted to.
All right, great to learn, Robin. Thank you for the comment. So actually, I think that they're missing a fifth technique here by using KSQL in order to pass the data to BigQuery. So next time, that will be in as well. Yes, please.
Thanks for the interesting talk. My question would be, how do you handle schema changes in the whole process if you, at the end, store them in BigQuery?
OK, so I have a question for you. Are we talking about schema changes of the database, like he asked, or schema changes of your format?
Of the source data, for example.
All right, so Avro has a schema evolution. So basically, you can define which schema approach, which evolution approach you would like. It's backward compatible. So you can add records and do whatever needed. All the time we're adding fields to our messages, and schema registry handles it beautifully. And also with the connector that we worked with, the database table in BigQuery, the BigQuery native table, also updates automatically. So we don't even have to do anything until we break the schema completely. All right? Any more questions? Yes.
How do you test the entire pipeline?
Say again?
How do you test the entire pipeline?
How do we test the pipeline?
Yes.
Very good question. So this actually has a very long answer. So I think we should talk about it after the session because there are many different components here. And these have to be tested in many ways. First of all, we have to do unit testing to each and every part of the pipeline. And then some big integration tests on top of the approach that you choose that handles it end-to-end, from the event creation until it's been ready to analysis. And also, you want to have it on a reasonable time, in our case. Yes, please.
Getting some exercise. What was the latency?
All right, the latency, I'm talking about near real-time latency. Near real-time means up to a few seconds. So I guess it was something like 2, 3, 4, 5, depending on the actual load of the system. I think sometimes it was more than that, but I didn't see something like was above 10 seconds. So, any more questions, please?
Can I ask one?
Sure.
I have one question. So you talked about using Maxwell for the change.
Do you need the speakers or they will hear you? No, I'll repeat the question.
Okay.
Let's
so
go.
You talked about using Maxwell.
Yes, correct.
Did you look at Debezium as well?
Yes. We have the question was about Kafka Connect, using Kafka Connect for change data capture. So we have looked at Debezium as a Kafka connector that works perfectly with Kafka and streams the change data capture events to the analytics system. The reason we decided so far to use Maxwell, and we're still considering it, is that the time that we examined it, we saw that when using Debezium, you have to insert a record of the update timestamp for each and every table. And as we have databases that are a long way through, we didn't want to add a new field and add the actual code that updates the timestamp of each change, which was a condition for using Debezium for change data capture.
Yeah, that's definitely changed since, so now it's just based on the bin log. So it's,
all right, so now it's based on what? Please tell us.
On the bin log in MySQL.
All right, so currently Debezium is log-based similarly to Maxwell.
Exactly.
Great, so good comment, and we'll check it out. Any more questions? All right, thanks a lot, guys. Rate the session.